Good to all of you, my lovely students. So, as per the before class, already we have discussed about the combinational circuits. And as per the before class, the meaning of combinational circuit is the circuit which has no memory capacity, no feedback, and present output depends upon the present input. That type of circuits are basically known as the combinational circuits. And also we have discussed the different examples of combinational circuits. And basically the most important examples are the adder, subtractor, multiplexer, demultiplexer, encoder, decoder, so on. So out of these combinational circuits, let us discuss today about the one type of combinational circuit named as the binary adder. The binary adder, from its name we can define the definitions. So as per the name, it is one type of adder that can add the binary numbers. Simply if we take the name of adder, then that is also the meaning is same as we can add. But in this case the special name is binary adder. So accordingly it can add the binary numbers. And basically it is under the combinational circuit category. And it performs binary addition only. Since the name is binary adder, it can perform only the binary additions or it can add the binary numbers. Then next, basically the two binary numbers to be added can be designated. One is named as the agent and another is known as the addend. Basically the upper number is known as the agent and the lower number to be added is known as the addend. This fundamental is same as per our basic mathematics. Then this binary adder is classified into two categories. One is known as the half adder, another is known as the full adder. If we consider about the application of binary adder, then we can get the application in most of the arithmetical circuits like ALU within our computer system or within the digital computers, digital calculators, in microcontrollers, in PLC, and in timers also. So in different digital devices, mostly the arithmetical digital devices, we can get the presence of binary adders. Out of the two binary adders, let us discuss about the half adder. Half adder, basically it can add two binary bits at a time. It has the capability to add only two binary digits. That means it can add two numbers and each number is of single bit. It cannot add the two binary numbers having more than one bit. It can add only single bit binary numbers or it can add two binary bits. So accordingly, it has two inputs. One is known as A, another is known as B, and two outputs. One is known as the sum or result bit, another is known as the carry. Suppose after addition of any two bit, we get an extra bit. That extra bit is known as the carry bit and the LSB bit is known as the sum bit. This can be verified from the truth table. From the truth table, since we have two inputs, accordingly 4 states we can get 0, 0, 0, 1, 1, 0, 1, 1. As per the manual process, now we can finish the filling of our truth table. When you add 0 plus 0, you must get result 0 and no extra bit means your carry must be 0. 0 plus 1. 0 plus 1 is equal to 1. So no extra bit, accordingly the carry bit will be 0. Then next 1, 0. 1 plus 0 is equal to 1. No extra bit, accordingly carry equal to 0. But while we are adding 1 plus 1, our result will be 1, 0. So here we get one extra bit 1 that is taken as the carry and the LSB bit in a 1, 0, 0 is known as the sum bit. In this way our half adder is operating. Truth table is a such type of table. Actually that table indicates the complete operation of a device. In digital electronics, actually truth table completely represents or completely display the total working process of any logic device. Only we have to implement the logic circuits as per the truth tables, unless truth table is clearly indicating the working principle. Then from the truth table, we have two outputs, one is sum and another is carry. So we can take one K map for sum and another K map for carry. The number of K maps for a device depends upon the number of outputs. Here we have two outputs, accordingly two K maps we can take for simplification. First K map is for sum, that can be used for simplifying the sum, and another K map is for the carry, for simplifying the carry. But in this case, you can see from the K map, it is very clear that there is no grouping possibilities. That means already simplified forms available, and we can write the SOP expression directly from the truth table. No grouping means simplification is not possible, already last position. So if we write directly the Boolean expression from the truth table, or we can write the Boolean expression from the K map, then for which we are getting the high output, only we have to take the min terms against those high outputs, and we can add the min terms and we can get the Boolean expression for the S and carry. Or unless, as per the before class, already you have discussed or already you have finished how we write the Boolean expression from the truth table, or how we write the Boolean expression from the K map. We can follow that process and we can write the Boolean expression. Following that process, the Boolean expression will be for S is equal to A bar B plus A B bar, and for carry equal to A B. Then next step, we can implement the logic circuit by seeing the Boolean expression. It is not required to practice the logic circuit for each device and to memorize. Directly seeing the Boolean expression, how you implement the circuit, please remember that will make you design any circuit or implement any digital circuit by seeing the truth table. So from the Boolean expression, the expression for sum is A bar B plus A B bar, which is the same as the A XOR B. So accordingly, the logic circuit for sum is simply consisting of an XOR gate, and we can check from the logic circuit. Simple XOR gate having two inputs A B, and then accordingly we get the sum. Similarly, the logic circuit for carry is AB. AB means A into B. So simply use one AND gate having two inputs AB, then we get the AB. That will be the carry output. The logic circuit simply consisting of an XOR gate and an AND gate. The two outputs, one is sum and another is carry. The half adder symbolically can be represented by a square as given in slides. Simply by a square having two inputs and two outputs. Next we discuss about the full adder. Full adder is a such type of combinational circuit that can add three binary digits at a time. Half adder, 2 bits can be added, but in full adder, 3 bits can be added at a time. The 3 bits means it has 3 inputs, and we can name the 3 inputs as A, B and C in, and two outputs named as sum and carry. The two outputs sum and carry is the same as in before case, same as the before device half adder, but here the input number is 3, but in case of half adder you have 2 inputs. Then next we discuss about the truth table. Since 3 inputs, accordingly we have 8 states starting from 0, 0, 0 to 1, 1, 1. For each state we have a sum output and also a carry output. So sum output and carry output, how we determine? If we can able to determine the values manually, it is not required to practice the truth table or to memorize the truth table by reading repeatedly. We can write the truth table by manual process, then that truth table can be implemented to logic circuits. So let us check any 2 to 3 state, then rest state you can try. First state is 0, 0, 0. So add manually or by pen and paper 0 plus 0 plus 0. Already we have a chapter binary addition. So we can use that fundamental 0 plus 0 plus 0. We get 0. No extra bit means carry also 0. Second state 0 plus 0 plus 1. By using the simple binary addition process, we get sum 1 and carry 0. Accordingly, we can proceed for the each step and check the seventh state 1 1 0. 1 plus 1 plus 0. 1 plus 1 plus 0 is equal 1 plus 1. First of all, we have to add 1 plus 1 1 0. 1 0 plus 0 equal to 1 0. The result is 1 0. Total result. Out of this total result 1 0, 0 is taken as the sum bit and 1 is taken as the carry bit. Similarly, for the eighth state 1 1 1, 1 plus 1 equal to 1 0, 1 0 plus 1 equal to 1 1. The total result is 1 1. Out of this 1 1, the LSB 1 is taken as the sum bit and the MSB 1 is taken as the carry bit. So in this format, we can able to write the truth table for full adder. Not required to memorize. Be careful. Binary addition process already with you, and you can use that process and you can finish the writing of truth table. Then next step after writing the truth table, as per the basic fundamental in Karnaugh map system, we can implement or we can convert the truth table to K-map. How we put the truth table within the K-map, we can use that fundamental plotting of K-map from the truth table and then using the simplification process. But first of all, we have to put the truth table within the K-map. One K-map will be valid for the sum, another will be for the carry. The how we put already finished in the class K-mapping. Again, take the review. You have to write 1 within the corresponding square for which your output is 1 in truth table. For which state your output is 1, you have to write or plot or put 1 in that square. So accordingly, now you can check your K-map and then start simplification by K-map. If you search the K-map for sum, further simplification is not possible because all the minterms are individual, no grouping format. So accordingly, the simplified Boolean expression for sum, we can write directly the minterms of each combination and add the minterms. For example, the 4 minterms for which your output is 1. Directly take the minterms and add those minterms. You get the SOP expression for the sum. And that SOP expression is equivalent to A XOR B XOR C in. Then next, search the K-map for carry. For carry, we can make some groups and simplifying the groups, we can get the simplified Boolean expression for carry AB plus C in into A. Then next we try to implement the logic circuit by considering these Boolean expressions. As for the basic fundamental, how we convert or how we implement any type of Boolean expression to a logic circuit, here also you can take the Boolean expressions and directly you can design your circuit or implement your circuit without repeated memorization. So this is the symbol all over about the symbol of full adder, and also the all over about the basic discussion about the half adder and full adder. But if we search in practical life, is it the real fact always we are facing addition of only 2 bits or addition of only 3 bits? No. In practical life, there may be the chance, not maybe, sure. You must face the condition you have to add 2 binary numbers having more than 1 bit or more than 2, 3 or 4 bits. Your two binary numbers to be added maybe of 4 bit each, or maybe 8 bit each, or maybe 16 bit each. So if you try to perform the addition of, for example, 2 4-bit numbers, while you are trying to add 4 8-bit numbers, when you try to add 2 binary numbers having 4 bit each, then what you have to do? As per this discussion, half adder means it can add only 2 binary bits. That means it can add 2 binary numbers, each one having 1 bit. Similarly, full adder capability is it can add 3 binary numbers and each one having single bit. But when your purpose is to add 2 binary numbers and each binary number has 4 bit, for example, in this case, you have to take number of full adders and you have to connect properly in such a manner that directly you have to apply the 2 numbers, 4-bit numbers, and you can get directly the results. So in that case, the adder name is parallel binary adder. Parallel binary adder. So while we are trying to perform addition of 2 binary numbers having more than 1, then it is not possible by the half adder and full adder. And if we consider a standard number of 4 bit, then to add 2 binary numbers having 4 bit each, we have to basically take 4 full adders, and those 4 full adders are connected in such a manner that at a time you can apply the inputs, first input of 4 bit, then second input of 4 bit. That means suppose we consider A is 1 input and B is 1 input. A carry 4 bits and B also carry 4 bits. At a time we can apply, that means A has 4 input lines and B also has 4 input lines. And we can apply the inputs directly at a time, then we can get the result at a time. And that adder is basically known as the 4-bit parallel binary adder. Similarly, suppose your purpose is to add 2 binary numbers A and B, and the number of bits in binary number A is 8 bit, and suppose the number of bits in binary number B is 8 bit. So now you have to add 2 binary numbers of each number having 8 bit. So in that case, also considering the 8 number of full adders, we can design that circuit, and that logic circuit is known as the 8-bit parallel binary adder. So this is the purpose of our next class. In next class we discuss all these designs: 4-bit parallel binary adder, 8-bit parallel binary adder. Similarly, you can take any example: 5-bit binary parallel adder, 3-bit parallel binary adder. So for constructing all those adders, we have to take the combination of full adders. Accordingly, the full adder is the basic building block of any other adders. And this is for the today's class. Next, we consider the similarly we can discuss the definition, the truth table, the logic circuit, and from the logic circuit the Boolean expression, from the Boolean expression how we implement the parallel binary adder. Next class we can design the different circuits. So finally, for the next class, the introduction is already discussed, and let us stop today. Next class, be ready, and if you try to search any preliminary idea about the parallel binary adder, you can also search, and be ready for your next class. Thanking you.